Hi, my name is Hassan. Today I will be presenting Crow, which is a substrate that enables mechanisms for improving DRAM performance, energy efficiency, and reliability. This work is done in collaboration with co-authors from ETH Zurich and Carnegie Mellon University. DRAM offers high memory capacity at low cost. However, process technology scaling introduces three key challenges to DRAM. First, high DRAM access latency is a bottleneck for improving system performance and energy efficiency. Second, as the number of cells in a DRAM chip increases, DRAM refresh incurs more performance and energy overheads. Third, as process technology shrinks, DRAM cells become smaller and get closer to each other. The increasing interference between cells exposes DRAM to vulnerabilities such as RowHammer, which reduce DRAM reliability. To overcome these scaling challenges of DRAM, we develop a low-cost substrate, which we call copy row DRAM or CROW. The key component of the CROW substrate is a copy row, which CROW introduces to a subarray in addition to the conventional regular DRAM rows. A copy row incurs a small area overhead, and it has three benefits. First, data can be efficiently duplicated from a regular row into a copy row. Second, data duplicated to a regular and copy row can be accessed much faster than only a regular row. Third, a regular row can be remapped to a copy row. We use CROW to develop mechanisms to address the scaling challenges of DRAM. We develop and evaluate CROW cache, which enables in-DRAM caching to reduce access latency, and CROW ref, which reduces the performance and energy overhead of DRAM refresh. According to our evaluation, the two mechanisms together improve system performance by 20% and reduce DRAM energy by 22% on average. We also propose a third mechanism for mitigating the RowHammer vulnerability. We'll leave evaluation of this mechanism for future work. We believe CROW will enable many other use cases going forward. This is the outline of today's talk. I will start with describing the basics of DRAM. Here I show a typical system with a CPU and a DRAM module that has several DRAM chips. Inside the DRAM chip there are multiple subarrays, which contain many DRAM cells organized as a two-dimensional array. A DRAM cell stores a single bit of information as electrical charge. In a subarray, the cells are vertically connected to sense amplifiers, which can read the data from the cells and update it if needed. A row of DRAM cells is called DRAM row. Now let's take a look at DRAM commands that the memory controller issues to read data from a particular DRAM cell. To perform an access, the memory controller first activates or opens a row by issuing an activate command. Activate causes the cells of the selected row to share their charge to the sense amplifiers. Based on the charge amount received, the sense amplifiers determine the value that each cell stores, and then they restore the charge of the cells back to its initial amount. After row activation, the memory controller issues a read command to the DRAM. With that command, the data is read from the corresponding sense amplifier and transferred over the memory bus to the CPU. Although the memory controller has received the data, it still needs to perform one more operation to prepare DRAM for future access to a different row. The memory controller issues a precharge command to close an open row. The precharge operation turns both the row and the sense amplifiers back to their initial states. This is basically how DRAM is accessed. Now let me explain how we slightly modify DRAM to implement the CROW substrate. As I explained at the beginning, DRAM scaling leads to these three key challenges: access latency, refresh overhead, and exposure to vulnerabilities such as RowHammer, which reduce DRAM reliability. Our goal in this work is to develop a substrate to overcome the DRAM scaling challenges by duplicating and remapping data within a subarray. However, it's not possible to duplicate and remap data in current DRAM. To enable that, the CROW substrate implements two key components. First, CROW slightly modifies the DRAM subarray by introducing copy rows in addition to the regular rows in conventional DRAM. A copy row is composed of the same DRAM cells a regular row is composed of. Different from the regular rows, copy rows have their own address decoder. This enables a copy row to be activated independently from a regular row. This property is useful for enabling two operations that I will explain in the next slides. Second, CROW implements a small table in the memory controller to store information related to operations performed on copy rows. Let me show you next what this substrate is useful for. The first of the two operations that CROW enables is copying the content of an entire regular row into a copy row. To initiate the row copy operation, the memory controller issues the new ISCA' command that the CRW substrate provides to the DRAM. This command first activates a regular row. After the data is latched in the sense amplifiers, the command activates a copy row. This results in the sense amplifiers writing the data of the regular row to both of the open rows. Let me explain how data is copied from one row to another within DRAM in more detail. For simplicity, let's assume in this slide that DRAM rows have only a single cell. Here, our goal is to copy data from the source row to the destination row. There are 5 steps involved. First, the source row is activated. Following the activation, the source row shares its charge with the sense amplifier. Then the sense amplifier starts restoration. At this point, CRW enables the destination row, and this results in the sense amplifiers restoring both rows to the same value of the source cell. So CRW enables quickly copying a regular row into a copy row. The second operation that CRW enables is simultaneously activating a regular row and a copy row. The memory controller performs multiple row activation by issuing the other new command act_t. When a regular and copy rows are activated together, if the two rows contain the same data, this operation results in low latency activation. Let me explain why in the next slide. Simultaneous multiple row activation operates similarly to the row copy operation. The difference is that two rows containing the same data are activated simultaneously. Doing so, both rows share their charge with the sense amplifiers. This accelerates charge sharing as two cells together share more charge with the sense amplifier. As a result, the restoration completes sooner and read-write operation can be serviced sooner compared to conventional single row activation. The CRW substrate enables fast access to data that is duplicated across a regular and a copy row. Now we have the substrate, but how can we benefit from it? The first mechanism we develop is CRW cache. We use CRW to address the high access latency problem of DRAM by implementing CRW cache. The key idea of CRW cache is to enable low latency access to the most recently activated regular rows in every subarray. CRW cache reduces latency by using both operations that the CRW substrate provides. First, it uses row copy to copy a newly activated regular row into a copy row. Second, it uses multiple row activation to activate the regular row and the copy row together on the next access. When a recently activated row is cached in DRAM, CRW cache activates it with 38% lower latency. Let me walk you through an example to show how CRW cache works. You see the CRW subarray and the CRW table from the previous slide. On the right-hand side, we show the queue of the requests to be serviced, which is initially empty. In this example, we first get a load request to address X. Since the CRW table is initially empty, the request misses in the CRW table. To enable fast access in the future, CRW cache allocates a copy row for the regular row that corresponds to address X. Then the memory controller issues an act_c command to perform the row copy operation. Then, let's assume DRAM receives requests to other rows causing bank conflicts, which forces row X to be closed. In the future, when the request queue receives another request to address X, the memory controller finds that X hits in the CRW cache and thus issues act_t to perform a low latency access. This is basically how CRW cache reduces DRAM latency when accessing a row for the second time. Now let me explain how we mitigate refresh overhead using the CRW substrate. DRAM refresh operations have high performance and energy overheads, and weak rows prevent reducing the refresh rate. Here we define a weak row as a row that has at least one cell that cannot retain data correctly when the refresh interval is increased. We use the CRW substrate to implement CRW_ref, whose key idea is to reduce refresh rate by remapping a weak regular row to a strong copy row. CRW_ref uses the row copy operation to remap a weak regular row to a strong copy row. Doing so, CRW_ref doubles the refresh interval, or in other words, eliminates half of the refresh requests that the memory controller must issue. Let me explain how exactly CRW_ref operates. The operation of CRW_ref is simple. CRW_ref uses a DRAM retention time profiling mechanism to discover weak rows and stores the remapping information in the CRW table. When the memory controller needs to activate a row, it first checks the CRW table to see whether the row has been remapped. If so, it activates the corresponding copy row instead of the weak regular row. To make this mechanism work, one question we need to answer is how many weak rows are typically there in a DRAM chip. It turns out that the weak rows are actually very rare. Here we assume a cell to be weak when it cannot retain data for 256 milliseconds. Prior work reports on DDR3 when the refresh interval is changed from the default 64 milliseconds to 256 milliseconds. Only about 1000 cells in a 32 GB DRAM module fail to retain the data correctly. Based on this information, we calculate the probability of having a subarray with different numbers of weak rows. The figure plots the probability of having a subarray with at least n weak rows. Although the probability of having a subarray with at least 1 or 2 weak rows is quite high, the probability rapidly decreases when we consider more weak rows. This motivates that even a small number of copy rows in a subarray are very likely to be sufficient to remap all weak regular rows. To detect weak rows, there are several prior works that propose DRAM retention time profilers. CrowRef can adopt any of these profilers. A profiler can either be used at system boot or during runtime, as Crow supports the Crow table to be updated at any time. So only a few copy rows are sufficient to halve the refresh rate. Let me now tell you about the third mechanism. In addition to CrowCache and CrowRef, in the paper we also briefly discuss a third mechanism that uses Crow to mitigate RowHammer errors. RowHammer is a vulnerability caused mainly by process technology scaling. As the DRAM cells become smaller and get closer to each other, they become more sensitive to electromagnetic interference. RowHammer errors are basically induced by rapidly activating and precharging a row. This operation disturbs the cells in neighbor rows and has a chance to flip some of the bits stored there. For mitigating RowHammer errors, our key idea is to use the Crow substrate to remap the victim rows to copy rows. This protects the data in the victim rows as the rows get physically moved away from the aggressor row. Please see our paper for a more detailed description of this mechanism. We'll leave the evaluation of this mechanism for future work. Now I will move on to the evaluation. To evaluate the Crow mechanisms, we used Remulator, which is a cyclically accurate DRAM simulation tool. The source code of our simulation infrastructure will be available in July. We analyze workloads from 4 benchmark suites, including Spec CPU 2006. These are the system parameters, and we implement Crow with 8 copy rows per subarray by default. Let me start with showing the performance and energy benefits of Crow cache. The figure shows the average speedup that Crow cache provides for single-core and 4-core workloads. For both, Crow cache provides 7% speedup, which is very close to an ideal hypothetical mechanism with Crow cache that has 100% hit rate. Crow cache also saves DRAM energy, mainly because of reduction in execution time. So Crow cache improves single-core and 4-core performance and energy. Let me also quickly show the performance and energy benefits of CrowRef. CrowRef eliminates many of the DRAM refresh requests, and this leads to 7% speedup for single-core workloads and almost 12% speedup for 4-core workloads. Eliminating many refreshes also saves significant DRAM energy. CrowRef significantly reduces the performance and energy overhead of DRAM refresh. CrowCache and CrowRef are complementary to each other. We combine both mechanisms by keeping 8 copy rows per subarray. Both mechanisms together provide 17% and 20% speedup for single-core and 4-core workloads, and they perform close to an ideal mechanism that has a Crow cache with 100% hit rate and eliminates all DRAM refresh operations. Crow cache and CrowRef together save significant DRAM energy. The mechanisms perform well when combined with 8 copy rows per subarray because neither of the mechanisms utilize all of the copy rows in many cases. For example, as I have shown previously, it is very unlikely to have too many weak rows in a subarray, so CrowRef does not make use of majority of the copy rows. We conclude that CrowCache and CrowRef further improve system performance and DRAM energy when combined. Crow incurs modest overheads in the DRAM and the memory controller when using a configuration with 8 copy rows per subarray. Please see the paper for a more detailed hardware overhead evaluation. Please also see our paper for more detailed evaluation. There we have sensitivity studies to the number of copy rows per Subarray, chip density, and last level cache capacity. Also, we evaluate Crow cache with a strat prefetcher, and we compare Crow cache to two prior works that also enable in-DRAM caching. Let me quickly conclude now. We propose Crow, an in-DRAM substrate for addressing the three key challenges of DRAM scaling. Crow introduces copy rows in addition to regular rows in conventional DRAM. A copy row provides three key benefits. Using the Crow substrate, we develop Crow cache to enable in-DRAM caching, Crow ref to mitigate DRAM refresh overhead, and a mechanism for mitigating RowHammer errors. We believe Crow will enable many other use cases going forward. Thanks for your patience. Please contact me if you have any questions.